Good morning, professors from the scientific committee. We're Mok Chun Hei and Wong Hei from Shin Kong Hui Cheng Siu Tim Secondary School, and our topic today is least optimal square pecking in a square. Square pecking is an open problem in mathematics. It aims to find the minimum side length of a square container that can bound some configuration of n unit squares. In our research, we investigate the opposite problem. In least optimal square pecking, we try to find the minimum side length of a square container Sn that can bound all configurations of n unit squares. For example, a square container of side length 3 and root 5 can bound these two configurations, but a container of size 2 cannot bound the second one. In fact, S2 is exactly root 5, as we shall see. Now, to find Sn, there are two steps. First, in order to show a lower bound, we have to find the minimum square container size of a specific configuration of n squares. Then, to show an upper bound, we have to prove that all configurations of n squares can be bounded by a square container of a specific size. Together, the exact values of Sn can be found. We call a set of n unit squares an n configuration, and to make the problem interesting, we have to restrict that the squares can't overlap and have to be connected, meaning that there's a path connecting each pair of unit squares. Great. After we've defined our problem, let's first discuss some properties of a square container. For a set of point S, let's define dsR be the size oriented along a direction R as shown. This allows us to define FSR, the size of the square container of S oriented along a direction R, as the maximum of the two side lengths of the bounding rectangle, dsR and dsR perp, where R perp is the vector perpendicular to R. Finally, we can define F as min. We can define F as min, the size of the smallest square container, be the minimum of Fs across all orientations R. Then we can rephrase our problem as finding the maximum size of the smallest square container, F lambda min, for all n configurations lambda, shown here in green. A crucial observation regarding the smallest square container is that either the configuration touches all four sides of the container, which we call case alpha, or one of the sides of the container attains a local minimum, which we call case beta. We realized from numerical simulations that the alpha case usually results in F lambda min closer to S2 than the beta case. It turns out that it's helpful to choose an orientation that makes an alpha container, a tight square container. Now, let's apply the above techniques, properties to finding S2, the minimum container size that can bound all two configurations. We'll perform numerical simulations first to acquire an estimate of S2, which is about root 5. Let's now prove this rigorously. This is the least optimal 2 configuration. By considering a rotating container, we can compute F lambda R as a function of the angle of the container orientation R. We found that F lambda has a minimum of root 5, which provides a lower bound for S2. Next, to find an upper bound of S2, first notice that every 2 configuration is congruent to this diagram for some values of parameters y and theta. Now, we pick R be the orientation along a square passing through the points A, B, G, H. This is an alpha container. After some calculus, it can be shown that the size of this square container is no larger than root 5. This is an upper bound of S2. Combining the upper and lower bounds, we found that S2 equals root 5. After investigating the case of n equals 2, let's expand our scope to the largest values of n. To better understand a general n configuration, we'll classify the intersection of the configuration and the container, and we'll continue to focus on alpha containers. These are the classes we identified. We'll start from the top, which is class alpha 4. When each edge of the container has at least one intersection point with the configuration, we'll call this alpha 4, so the right one here. In addition, we define 3 subclasses of alpha 4, namely alpha 4.2, 4.3, and 4.4. The number represents how many squares touch the 4 sides of the container. Finally, alpha 4.2 can be further classified into 3 types based on the minimum length L between the 2 squares of the container, 2 squares that touch the container. For example, in class alpha 4.2 type 1, L connects the vertex adjacent to theta and opposite to phi. Now that we've classified the configurations, the next thing to do is to find the maximum container size for each class. For class alpha 4.2, we'll use the technique of reducibility. In this class, we'll call a configuration reducible if there is another configuration with equal container size but a smaller L. Is it possible to, in some sense, ignore reducible configurations? Let's illustrate by plotting some configurations. Theorem 5.9 states that if an increasing function, UL, bounds the container of all irreducible configurations, the black dots here, then UL also bounds the reducible ones, the red triangles. This means that reducible configurations do not affect the upper bound. This theorem can be proven by the properties of reducibility and continuity. Now, let's identify some reducible configurations. Consider when we slightly increase and decrease the angle theta. If we can change theta in the direction that reduces L, then the configuration is reducible. This is always possible unless L is at a local minimum. Therefore, when we consider irreducible configurations, we can apply the condition of local minima and, using lemma 5.12, impose a restriction in the configuration's geometry. How are these techniques used? We'll now apply them to find the maximum container size of class alpha 4.2 type 1, which looks like this. To start, we'll focus on an irreducible configuration and write equations based on two conditions, namely that L is at a local minima with respect to both theta and phi, and that the container is a square. This allows us to solve for the exact values of theta and phi, and find out the container size is L over root 2 plus root 5, which crucially is an increasing function of L. Hence, by the reducibility theorem, the reducible configurations, which wasn't considered, do not affect the maximum container size. End of proof. Class alpha 4.2 type 2 and 3 can be handled similarly. Great, now we've tackled class alpha 4.2. For alpha 4.3 and 4.4, we'll use another technique, which we call path rearrangement. The problem with these classes is that the connection of squares can be very complicated, but when you look at them, they seem to not spread out as much. They pack squares more efficiently. Thus, the key is to omit unnecessary details in the configurations. Let's take a look at class alpha 4.3. We have to prove this container is smaller than a container of class alpha 4.2. We can find a path K1 from Q0 to Q1 and a path K2 from Q0 to Q2. Furthermore, let QC be the last common square of the two paths. We'll then deduce cases based on how K1 and K2 split. The three cases are when QC is Q0, QC is Q1, or neither. Next, for each case, we'll perform transformations to the diagram while fixing the container size. You may wonder how this case is transformed. Well, first, we replace the squares along the path with line segments as shown to simplify. By counting the number of squares, we get an inequality. And finally, the way we defined QC means that we didn't double count when we summed up the lengths. Then we replace these two line segments with the line segments shortest between the square and the edge. Now comes the rearrangement. We'll swap LS perp and QC as shown. And after further swapping LR perp and QC now touches the two sides of the container. Finally, we replace all the line segments with one like so, and voila, without changing the container size, this is now of class alpha 4.2, with an L small enough to prove our claim. Class alpha 4.4 is handled in the same way. We've handled all the classes, so lastly, let's summarize and derive the general formula for Sn. Since it can be shown that any configuration can be contained in an alpha 4 container, by exhausting all the classes of alpha 4, we've proven this upper bound of Sn. What about the lower bound? This requires finding the least optimal configuration, which is this configuration of class alpha 4.2 type 1 with the middle n minus 2 squares connecting with each other vertex to vertex at right angles. It can be shown that its minimum square container size, f lambda min, equals n plus root 5 minus 2. This serves as our lower bound. Therefore, we've reached our main result. All n configurations can be contained in a square of side length n plus root 5 minus 2. This result is quite surprising, given that the problem of most optimal square packing is still open and very difficult. And this is quite an exact and simple formula in our opinion. To sum up, we found S2 using the idea of a rotating container. Then for n at least 3, we classified how a configuration can intersect with a square container. Next, we applied the technique of reducibility to class alpha 4.2 and the technique of path rearrangement to class alpha 4.3 and 4.4. We finally found the least optimal configuration and obtained the general formula for Sn. In the future, the methodology developed here may be useful in the study of packing other shapes in 2 or even higher dimensions, like regular polygons, rectangles of a certain ratio, or even cubes and hypercubes. Thank you.